let us solve some numerical examples in case of power law. So this is example 2.11. Find the relative error in Z, and Z is given as a to the power 4, b to the power 1 by 3, c d to the power 3 by 2. So again we will use delta Z upon Z. So what is power here? Power is 4. 4 into delta A upon A. What is power here? 1 by 3. So plus 1 by 3 into delta B upon B. Now C is in division, but power is 1. So directly we will add delta C by C. What is the power of D? 3 by 2. Though it will become minus 3 by 2, but we always add. So power 3 by 2 into delta D by D. So in this way we calculate the error when we have a formula which involves power function. Example 2.12. The time period of oscillation of a simple pendulum is given by T is equal to 2 pi under root L by G. Measured value of length is 20 centimeter. So this is value of L known to 1 mm accuracy. So this is known to be 1 mm accurate. So our value is 20.0 plus minus 0.1 centimeter because it is 1 mm. Also we can see this last digit. Last digit is always uncertain. And the time for 100 oscillations of the pendulum is found to be 90 seconds. So this time period is found to be 90 seconds using a wristwatch, and this wristwatch has 1 second resolution. So this 90 second is equal to 90 plus minus 1 second. Also if you observe, there is no digit after decimal, there is no decimal point. So that means it is plus minus, this last digit is uncertain, that means plus minus 1. What is the accuracy in determination of G? So we have to calculate what is the accuracy in determination of this gravitational acceleration. Now let us adjust this formula. So we have T is equal to 2 pi under root L by G. So squaring both the side, so we get T square is equal to 4, 2 square is 4, pi square L by G. So this is our formula. Let us take G this side. So what we get? 4 pi square L by T. So G is equal to 4 pi square L by, sorry, this T square. So this is our formula. So now let us calculate what is error in G. G is equal to 4 pi square L by T square. Now here this is T. How do we calculate this time period? Time period is total time taken by number of oscillations. So number of oscillations N is equal to 100. So delta T is equal to delta T upon N. Delta T upon N. Therefore delta T upon T is equal to delta T upon T. So let us solve this. The errors in both L and T are the least count errors. Least count errors because they are coming because of the least count of the wristwatch. What is the minimum duration that can be measured with the wristwatch? That is 1 second. That's why it is called least count of the wristwatch. What is the minimum value that can be read with the meter scale? That is 1 mm or 0.1 centimeter. So this is least count of the meter scale. That's why error is least count errors. Now let us see. So this delta G upon G is equal to delta L upon L plus 2 delta T upon T. So how do we get this formula? So you remember that if we have power function, then we use this kind of terms. But where is 4 pi square? Again, this 4 pi square is a universal constant. 4 is a number. There can be no error in a number. Also pi is a number. So there is no error in this number. So in any measurement, if we are given any constant, suppose we have given any constant, we will assume that there is no error associated with that number or constant. I am repeating again, if we are given a constant or a number, we always assume that there is no error associated with that number or constant. So there is no error in pi square, only error is in L and T. So let me write this. So what we have? We have L and T square. So again remember, using the same formula like this, delta Z upon Z type. So delta G upon G is equal to delta L upon L, because there is only single power, plus here we have 2 power, 2 delta T upon T, and this will have no error because this is a number and pi is also a number. Let us put the value. So delta G upon G, delta L upon L. So we have 1 millimeter, not 1 centimeter. So 0.1 centimeter divided by 20 centimeter. So this is in L. Now we have to tell that what is the error in delta T upon T. Here we have seen delta T upon T is equal to delta T, that means error in time measurement, that is 1 second, in upon total time taken, that means 90 seconds. So we have 2 into 1 by 90. After calculating, what we get? 0.027. Again this is relative error, this is relative because this is delta G by G. Now if we want to calculate percentage error, we simply multiply this with 100. So let us multiply this with 100. So 100 into delta L upon L plus 2 into 100 delta T by T, we get around 3% error. We get 3% error. Now next topic is significant figures. So we are hearing about significant figures for a very long time. Now let us understand what are significant figures or significant digits. So we have discussed that every measurement have some errors, and the result of measurements should be reported in a way that indicates the precision of measurements. So when we suppose we measure something, this length with help of a meter scale, so definitely least count of a meter scale is 0.1 centimeter. Then we should report it like 20.1 centimeter, not like this 20.100 centimeter, because this last digit is the least count of this. Suppose the same measurement we do with vernier calipers. With vernier calipers, this least count is 0.01 centimeter and we are measuring the same distance, then we will report it like 20.10 centimeter, because our measurement is accurate till this second digit of decimal. So that's why we are writing second digit. Suppose we use further fine instrument with this value, then how we will write? In that case we write 20.1100 centimeter, because our measurement is true up to 3 place after decimal. So that's why we are giving 3 digits after decimal. So this is important. So we should write or we should give the quantity in such a way that indicates how precise our measurement. So precision of the measurement should be indicated by that number. Normally the reported measurements in a number includes all the digits of number that are known reliably plus the first digit that is uncertain. So what is the meaning of this line? Suppose we are measuring this same distance. This is 20.1. Okay, so we are measuring with a meter scale. So what is least count? 0.1 centimeter, and we are saying this is 20.1 centimeter. So again, what is the least count that we can read with meter scale? 0.1. So this can be 20.1 plus minus 0.1 centimeter. So last digit is uncertain. Last digit can be 2, last digit can be 0. So this will vary from 20.0 to 20.2. So last digit is uncertain. So we always write all the numbers that are reliably known. So these numbers are reliably known. This is definitely 20. Plus only one digit, first digit, that is uncertain. So what is uncertain digit? Uncertain digit is 1. So we write all those numbers, those are reliably known, 20, and one unreliable digit, that is 1. This is way of reporting something. Suppose, let us take one more example. We are measuring something on a weighing scale. Minimum weight that can be measured on this is 1 gram. Okay, so 453 gram if we weight something. So last digit is definitely uncertain because it is plus minus 1 gram. So this could be 452 gram or it could be 454 gram. So but these two digits are perfectly, we are sure these are perfectly reliable. This digit is not very reliable, uncertain. So all the digits that are reliable plus one digit that is unreliable. This is the way to write anything. So we put the first digit that is uncertain, the reliable digit plus the first uncertain digit are known as significant digits or insignificant figures.